Okay, the theme is, can we determine an action ratio from a regulation, particularly key dip and hammer rise. So key dip is an input concept and then hammer rise is an output. And we would divide the output number by the input number and come up with a ratio. That's basically an action ratio. Now on this old Yung Chang action model, you can see I have a movable capstan here. I can slide it back and forth, and we'll use that later on to show you something. But for now, the front end of the key is set very carefully to a 10 millimeter dip, which includes 1 1/4 millimeters of aftertouch, and that was done using this fancy Renner aftertouch gauge. You'll be using this a lot in class. You will absolutely fall in love with it. I'll show you how that's used a little bit later, but for now we have 10 millimeters of dip all the way, and we have 2 millimeters of let off, and that was done with this Yamaha gauge. 2 millimeters, there we go. Now in order for this action to work, and by work I mean key goes down, hammer goes up, let off, and then drops. Now I made the drop a little extra so long so you can see clearly that it is disengaging. Right, now watch the back check and even the whipping body to a degree, and you will see that after the hammer disengages, the back check still rises, and so does the whipping body. Here we go again slowly. Okay, it's through, and you can see the system rising a little bit. That shows that the safety margin is definitely in place. Now the thing is, this action really calls for 46 or even 47 millimeters of blow, but only 43 will make it work. When it was set to 46, it didn't work. It got locked, it didn't have follow through, and didn't have any safety measures in at all, and you'll see that in a later segment. Alright, now is this a disaster? Certainly not. There are a lot of actions actually out there that this is what you end up with, and you know, that's not the worst case. I could increase the dip a little bit, but generally speaking, we don't want to do that. We want to keep the dip set where it should be, and in this case I've set it exactly to 10. So then, can the regulation numbers give us an action ratio? Well, certainly they can. If we have 43 millimeters of blow minus 2 millimeters of let off, that gives us 41 millimeters of actual hammer rise before it disengages. On the dip side, if we have 10 millimeters of total dip minus 1.25 millimeters of aftertouch at the end of the key, that gives us 8.75 millimeters of actual key travel at the end of the key before the key disengages in aftertouch. So we take the 41 divided by 8.75, and that gives us 4.68. So our action ratio is 4.7 rounded. Alright, now the question is, those are vertical numbers. The key goes down, the hammer goes up. But the action ratio from its internal composition includes what we call lever arms, which we'll get into a little bit later. But we have the front of the key, we have the back of the key, so we have an input arm and an output arm. Similar on the whipping, it has 2 arms, an input and an output arm, and the same thing on the hammer shank, a little input arm and an output arm. Now these are long, relatively horizontal measurements, and they work through the action ratio equation in such a way that they should give us a similar, if not exact, number that we got from these vertical numbers, and we will see how that works out a little bit later when we actually work through the action geometry program. Okay, so what I'm going to do is set the blow distance to what the manufacturer's spec is and show you that it's not working correctly. Alright, with the blow distance increased to 46 millimeters here. If we watch carefully, we can see that the hammer gets to escapement at let off. It barely gets through let off and drops very slowly, and basically it's locked. There's no safety valve here at all. Aftertouch needs to be increased in order for this to work better. We can do that one of two ways. We can raise the hammer back up to decrease the blow distance to 43 millimeters or so, or increase the dip. But we don't want to increase the dip. That's really the last thing you want to do when regulating action. So that's not going to work right there. Also, you can see that the back check, after the hammer barely escapes, the back check itself is locked. It just doesn't go any higher. So that's a visual clue right there that things aren't working right. And also, where the jack trips out, barely trips out, there's no space between the back end of the jack, back edge of it I should say, and the knuckle. They're pretty much in contact with each other there. So that just is not good. Alright, let's have a look at the front of the key. As mentioned earlier, the key dip is set to exactly 10 millimeters out here. In fact, you can barely see it, or maybe you can, but I have a capstan screw in place here so that I can really lock the dip and then take out any arbitrary sponginess that might exist. But Aftertouch, this is the Aftertouch gauge you'll be working with in class, and it measures 1 1/4 millimeters. And the way it's used is it's inserted above the punching and then press down and make solid contact, and then watch the hammer at the other end go through let off and drop. And I'll show you that with this in place that it is absolutely not. So I'll have to back up the camera again. Okay, now with the Aftertouch gauge in place, as you saw just earlier, I push it down until it makes solid contact, and you can see everything is just stopped right there. So, how do I make this work? Well, I'm simply going to turn the capstan in what direction? Well, we want to turn it up in this case. And as it does, you can see that I'm keeping solid pressure at the end of the key. Not crushing pressure, but just firm pressure. Turning this up until the hammer drops. You see that? Okay, I'm going to let everything down again. Go back up, do the same thing. A little bit more pressure, and there we go. Now it's working again, the way it should be. A little extra room because of Aftertouch, and you can see the back check rising again a little bit afterwards. And what does this blow now? We're going to be back to 43 millimeters. So that's how things work, and that's how you can determine an action ratio by working with regulation numbers only. And that's also the way you can make any action work, as long as you understand the little trick, little magic of working with the blow distance as you need to. Now, you may not like how things turn out on a particular action, but you have to make it work. Sometimes you increase the dip a little bit and decrease the hammer blow a little bit, but you have to make it work. If it has internal problems, it's an action geometry issue, absolutely, but at least you can make something work. Okay, I'm jumping ahead a little bit, but the action geometry program said in order to fix this action ratio, I needed to move the capstan back 3 millimeters, which I have right here. And so that changes everything really, and I am now able to get 46 or even 47 millimeters of blow. So I'll back the camera up and we'll see that. Right, so Don't know if it'll come out in the video, but now I have 46, pushing 47 millimeters of blow. So just that little move on the capstan fixed the problem. And so going through the system, we have let off and drop and a little extra to spare. So there we have it. Yes, Carl, I know it's too fast.